Hi, I'm Dr. J for Modern Statistics. In this video, I demonstrate how to interpret linear multiple regression output using SPSS. Most importantly, I focus on how to interpret accurately and in plain English the regression coefficient of each independent variable that has different measurement property. Whether you are reading a journal article, reviewing a master's thesis or PhD dissertation for your own studies, or just reading a methods textbook for your classes, you may sometimes find yourself a little frustrated because the authors of the book or the articles may not be fully interpreting the findings in layman's terms, which makes it a little difficult to understand, especially for the beginners. This video is to help researchers like you so that your own narrative in your own findings comes to life for your own audience. Now let's jump right in. Here I am with a data set that contains 5 variables. This is a shortened version of the full 2018 General Social Survey data, which is a nationally representative survey of adults in the US examining both their social characteristics and attitudes. The data are produced by a nonpartisan research institution called NYRC at the University of Chicago. These data are free and publicly available to researchers like you. So if you want to download the full version, the website to access the data directly is provided in the description below. The 5 variables, again, are income, education, gender, time spent in a bar, and attractiveness rating. So here is the research question. What are the predictors of how much money a person makes? In other words, what influences a person's income? Let's suppose that a rather crazy social scientist has proposed an outrageous regression model in which he hypothesizes that a person's income is determined by one's education level, gender, how frequently a person spends his time or her time in a bar, and how attractive the person is. Now, before we run this model, let's first examine quickly how each variable is measured so that we can interpret each independent variable's relationship to the dependent variable accurately. So here we are at the variable view in SPSS. Our dependent variable income is measured in constant dollars. So when we say 1 unit change, that 1 unit here would be $1. For education, it measures how many years of schooling a person has done or finished, and it's measured in years. For gender variable, this is a binary variable, sometimes called dummy variable, which has 2 values, male and female. Male is coded 1 and female is coded 0. The way we interpret the regression coefficient of a dummy variable is slightly different from that of a continuous variable. And I'll explain the difference when we get to the output in just a minute. And our third independent variable, time at bar, is measured on a 7-point Likert scale, ranging from never spending an evening in a bar, coded 1, to spending evenings in a bar almost every night, coded 7. Our fourth and last independent variable, which is a person's attractiveness rating, is measured using a 5-point Likert scale, ranging from 1 for very unattractive to 5 for very attractive, like Beyonce, Denzel Washington, or Taylor Swift. You get the picture. Now, I would assume that viewers of this video would know how to run the procedure. So let's quickly run that. First, go to Analyze and then choose Regression and choose Linear because we're running a linear regression. And in this linear regression window, we move our dependent variable income to the box that says dependent and move our 4 independent variables to block 1 of 1, since we're examining the effects of all independent variables at once in one basket. Now, once we finish moving all our variables, check the statistics button. Then in the statistics window, check confidence interval and click continue and click OK to run the regression procedure. Since the focus of this video is on interpreting the regression coefficient of each independent variable accurately, I'll limit our discussion of other elements such as collinearity diagnostics, descriptives, outliers, and so on for next time. And since we're testing this model in one simple step and not in a hierarchical step, we will not concern ourselves with the R-squared change in this video. Now, here's our regression output. Now, let's look at the model summary. When reporting how much of the variance or the fluctuation of the values of the dependent variable is explained by the model, we do not report R-squared. Instead, we report the adjusted R-squared. Now, before we talk about that, let me just spend a few seconds on R-squared. The R-squared shows 0.156. Now, to interpret this in percentage term, we multiply it by 100, meaning that 15.6% of the observed variability in income is attributable to differences in education, gender, time spent in a bar, and the person's attractiveness. But can we conclude that in the population, these four independent variables explain really 15.6% of the variance in income? Not really. Why? Because R-squared tends to overestimate the perimeter it is designed to estimate. So for example, let's say to this model, you want to add another independent variable that measures, say, how often a person goes to the bathroom on any given day and tries to predict income from it. Although I cannot possibly find a good reason why the frequency of going to the bathroom would have anything to do with a person's income, there's a chance that your R-squared may still go up despite the outrageous hypothesis, and it will never go down. That's when the adjusted R-squared comes in. The adjusted R-squared can actually decrease if you add more independent variables that have nothing to do with the dependent variable. So if you're trying to make a population inference, it is a good idea to report adjusted R-squared instead of just R-squared. Now, what about the standard error of the estimate? This is basically the standard deviation of the residuals, which tells us how far off the estimations of the outcome variable will be on average. So the interpretation in this finding is that the average discrepancy between a person's reported income in the data and the amount of income the model estimates for a person, given the person's education, gender, attractiveness, and the time spent in a bar, is 32,277.825. Now, in theory, if your regression model is successful, then the standard error of the estimate should obviously be smaller than the standard deviation of your dependent variable, which in our example is income. So to just check it out, we know that the standard deviation of our dependent variable is 35,034.814, which is easily larger than the standard error of the estimate reported here. Now, let's look at the ANOVA table, analysis of variance table. The overall model is significant, which is indicated by the significance column. The observed significance level is less than 0.001, which is less than the minimum threshold of 0.05. So we can reject the null hypothesis that there is no linear relationship between the dependent variable and all of the independent variables here. Now, this number right here represents the sum of squares explained by the regression model, and the number below it is the residual sum of squares, which means the variability of the dependent variable not explained by the regression model here. As boring as these terms may sound, our R-squared is actually based on these numbers. So if you divide the regression sum of squares by the total sum of squares, you'll get the R-squared. And you might be wondering about why the numbers look a little weird, like 1.487e plus 11. Not to worry. If you double-click the table in your SPSS output and put your cursor on the number, or double-click the number again on your SPSS output, then SPSS will show the full number with all the decimal points. Now, enough with this not so exciting part of the regression output, really. So to find out and understand how each of the particular independent variable relates to the dependent variable, let's scroll down to the coefficients table. Now, first things first, we see that 3 of our 4 independent variables meet the minimum significance threshold of 0.05 and are therefore significant predictors of how much an adult can expect to make in the US. For education, we have an unstandardized regression coefficient of 4,043.51. Now, the coefficient is positive, so we know that there is a positive relationship between education and income. But what does that mean in English? So as level of education increases, how much money a US adult makes also increases. Okay, we get that, but how much more exactly? So we use the actual coefficient to understand the magnitude of the impact that education has on income. Remember that education is measured in years, right? Years of schooling. So we say as the education level increases by 1 year, income is predicted to go up by $4,043.51. So again, every 1 year increase in education credentials, for example, is associated with an increase of $4,043.51. Now, here's a slightly different but much easier to understand way of interpreting the same coefficient. Now, pick two persons in the data. One person has 10 years of schooling, and the other has 11 years of schooling. So assuming everything else is the same about these two individuals, and we assume that the only difference between them is that 1 year difference in schooling, the difference in income between these two individuals then is $4,043.51, with the person that has one more year of schooling making that much more money compared to the person with one less schooling. What about gender? Remember that male is coded 1 and female is coded 0, and the coefficient is positive. So the relationship between gender and income is positive. But what does that mean? Gender is a binary variable that has two groups, male group and female group. So you might say 1 unit increase, just like the other independent variables, is associated with an increase of $13,190.10 in income. But what does the 1 unit increase really mean here? It's basically the estimated difference in income on average between the two groups, the male group versus the female group. And because the male group is coded 1, where the female group is actually the reference category and is coded 0, and the coefficient is positive, that means male adults are on average expected to make $13,190.10 more than female adults. Now, let's look at the time spent in a bar. Remember that this is measured using a 7-point Likert scale. So every 1 unit increase in time or evening spent in a bar is associated with an increase of $1,927.17. Now, this finding may sound a bit outrageous, obviously, but from a statistical standpoint, one could argue that people who spend more time drinking and or socializing in a bar in the evening more frequently than others make more money than others. Yeah, I know, it doesn't make sense and it almost sounds unfair. Well, I've never been to a bar, so I don't know what really goes on in there. So further research is obviously needed to persuade people like me that drinking in a bar indeed makes one richer. Now, let me remind you that I didn't apply any theory here, one way or the other, and that this is just a statistical exercise. Now, let's look at the variable attractiveness. This is measured using a 7-point Likert scale, ranging from 1 for very unattractive to 7 for very attractive. Right? So every 1 unit increase in the attractiveness scale is associated with an increase of $783.11. So holding all other variables constant, does being good looking pay off? No. Why? Notice the relationship is not significant. The p-value is 0.588, and since this p-value is surely greater than the alpha threshold of 0.05, which is where we draw the line between it being significant and not being significant, we say the relationship is not statistically significant. But just out of curiosity, what if we want to actually interpret the exact p-value of 0.588? Well, what does it mean? If we assume that the null hypothesis that the coefficient for attractiveness is 0 is true, then what are the chances that we would observe a coefficient as large as what's reported here, which is 783.108, purely by random chance? The answer is 58.8%, which is roughly 60%, and is too high that we are unable to reject the null hypothesis. But if the probability was low, say less than 0.05, which means the probability of seeing a coefficient that large by just pure luck is less than 5%, then we will take greater confidence in saying that it's relatively highly unlikely that this coefficient is a result of just pure luck, and we can then reject the null hypothesis. Now, we just interpreted each independent variable's relationship to the dependent variable based on the unstandardized coefficients. Let me ask you a question. If we draw another sample from the population using the same sampling methodology used for this data and test the same regression model as this one, will the unstandardized coefficients then be the same? Probably not. Why? Well, these unstandardized coefficients are what we call point estimate. These point estimates are likely to differ at least slightly from one sample to another. Well, if the coefficients are likely to be slightly different every time you draw another sample, then wouldn't you be interested in estimating a range within which we can be 95% confident that the true population parameter resides? The answer is given in the 95% confidence interval for B column. For example, for education, for every 1 year increase in schooling, you can expect that 95% of the time, there will be an increase of between $3,210 and $4,876.95. Now, I personally like using and reporting confidence intervals whenever and wherever I can because it shows how precise our point estimate really is. And people who peer review the quality of research articles are likely to give it more credibility if authors report confidence intervals in their findings table. Now, since the regression model is really about making predictions, let me end this video by exercising making predictions under a set of conditions. So for example, for someone who has 16 years of formal education, which is about someone with a 4-year college degree, and is a male and has never been to a bar and is very attractive, so a score of 7 on a 7-point scale, what would be the expected income for that person based on this data? Well, here is the basic equation based on the regression model. Now, all we have to do is provide the conditions. Plug in 16 years for education and plug in the value 1, as male is coded 1. And for time spent in a bar, plug in 1 because we're predicting income for someone who's never been to a bar. And for someone who's never been to a bar, it's coded 1. Okay? And for attractiveness scale, plug in code 7, which is the highest score representing those who are very attractive. Okay. So if you do the math, then the expected value of income for this profile comes out to be $49,793.94. So for somebody who has 16 years of education, is a male, and has never been to a bar, and who is very attractive, that person is expected to make $49,793.94. So this concludes our video on interpreting the coefficients of independent variables in a multiple regression output accurately and in plain English. For those who are learning how to use a software to run a regression model or learning how to interpret regression output in general for the first time, I hope this video was useful. And thank you, and I'll see you next time.